Hi there. Today I'm going to talk to you about magnetism and more specifically about an electromagnet. And we're going to discuss and go over finer points of the theory as what affects the strength of an electromagnet. Now, an electromagnet really can be broken down into three major components. The first one being the coil, and we're going to get into this a little bit later. We'll be talking about the body as well as the power source. Now, for the power source for today, I've taken the liberty of making myself this little holder that holds a series of 9-volt batteries, but I'm going to be playing with the amount of current that these batteries can deliver. Hence the reason why I've got them wired right now, or pre-wired with one side on the negative terminal in parallel with one another. But more on that later. Let's talk about the coil. The coil is made up of what we call diamagnetic material. Now that means that this is material that is not easily magnetized, but if I was to hook up the two leads of my coil to a power supply and run current through the coil, I am going to have a magnetic field. That magnetic field will extend in 360 degrees outwards, extending from the coil. But that magnetic field, or what we will call magnetic flux, meaning the flux density, the amount of magnetism that can emanate from the coil, is going to be considered relatively weak. And in just a second, I'm going to set up and wire this to my power supply, and I'm going to do a demonstration. Now, just to satisfy our viewers, I'm going to take a voltage reading of our battery pack, and what you'll see is that my batteries are actually just slightly below 9 volts. Technically, these batteries are dead, but they're still useful for the purposes of this particular demonstration. Here I've got the coil wired as a complete circuit to my power supply, but I've only got it hooked up to one of the batteries that's currently wired at 9 volts. And when I'm running 9 volts of current through the coil, you'll see that as I try and pick up these paper clips, the magnetic field just isn't strong enough to hold up these small paper clips. Now, according to our theory, if we increase the current flow to the coil, I'm going to increase the magnetic flux. And so what I'm going to do is I'm going to put two batteries in parallel. People that understand their theory about batteries, if I put two batteries in parallel, I'm going to increase the current. So I'm going to go ahead and add a little bit more current and wind it around the post without touching the other terminal, giving myself a little shock. Now, I now have two batteries in parallel, and I don't think I've really raised the current by all that much. Matter of fact, it's a little bit underwhelming. Let's continue the trend and increase the current once more. And we're back. Now I've got three batteries wired in parallel, so I've increased the current yet again. Now if I take the coil and I put it on the paper clips, we can see that there's an increase in the magnetic flux because I do have paper clips being held, but it's not taking all of them. So it's still weak. Let's try it again. Let's increase the current once more. As we continuously increase the amount of power that we're drawing from our little power supply here, I now have 4 batteries in parallel, and as I attempt to pick up the paper clips, we can see that there was a slight increase in the magnetic flux. I could be doing this all day and we would only see marginal increases. In order to really demonstrate how effective an electromagnet is, we need to introduce a core. By adding what we call a core, or a ferromagnetic core, what we're going to do is we're going to bring up the magnetic flux density from the coil. Now how does that work? Let me break it down. When we run current through the coil, we have magnetic flux or magnetic field that extends all the way around it. And when I take the coil and I introduce it to a ferromagnetic core, what happens is the magnetic flux of the coil is actually polarizing the magnetic domains of the core. What that means is right now the magnetic domains with no current running through it are in a state of disarray, and they don't have a magnetic flux of their own. But when I start running current through the coil, what we're going to do is we're going to polarize or align the magnetic domains of the core material. That means then that if the magnetic domains are aligned, it's going to have a magnetic field of its own. That magnetic field is going to add to the magnetic field of the coil. They become additive. And that's what brings us a lot more magnetic flux density. Here, I've set this up on the floor because I normally will do this in a classroom and I'll ask a student to demonstrate. I've got this section here. Once I apply power, I'm going to have an individual stand on either side and they're going to try and pull this apart. Now, because this will be magnetically coupled, I want to try and prove the theory that the strength of the magnetic field is proportional to its ampere turns. Now, what that means specifically is I can either choose to increase the number of turns in the coil to make a stronger magnet, or I can increase the amount of current. Well, the easiest way for me to do this is not by adding more turns. This has already been made, so I'm not going to play with this. What I'm going to do is I can easily adjust the current by having more batteries wired in parallel. And so this is where we're going to start. I'm going to reset my shot, and I'm going to have my participant who is going to try and pull these apart once we've wired it. Now, what we're going to do is I'm going to make the circuit. I'm going to wire it up. You should see, got to be careful not so these leads touch one another. And I'm going to add this section here. Oh, this is going to be good. Now, what I want you to do is I'd like you to put a foot on each side, okay, and with all of your strength, but I don't want you to hurt yourself.
Why?
Yeah.
Okay.
I would like you to try and pull this apart. Now, before we do anything, currently I have 5 batteries that are pushing about 8 volts, but 5 batteries wired in parallel. So I've got the maximum amount of current I could draw from these batteries. Let's see what happens.
Oh, goodness.
Okay, so there you have it. With all of his strength, he can't pull it apart. What we're going to do is we're going to reset, and I'm going to withdraw one of the batteries, so we only have 4 batteries, and we're going to try this again. Now, it's easy to just unwire one battery. Don't electrocute yourself. Okay, now let's try it again, but with only 4 batteries. So I've started to cut the current and take the current away. Go ahead. And are you pulling?
Yep.
Yep, yep. Okay, don't hurt yourself. No. Okay, it's not happening. Okay. So we're going to go from 4 batteries to 3.
Yeah. I think I got it.
And so by withdrawing batteries, what am I doing? I'm not affecting the voltage. What I am affecting is the amount of current flow. And this is what I want to try and prove. Go ahead, let's try this again. 8 volts, but with 3 batteries. Oh, so was that a lot harder or a lot easier?
Easier.
Okay. And what if we go down to 2 batteries?
I don't even need 2 hands.
Okay, well let's see. Bold words. Okay, with only 2 batteries now, wait, just so I don't get this. There. So we significantly weaken the amount of current flow. So, to recap, by cutting the amount of current flow, or the ampere turns, I've substantially weakened the magnetic flux density of my electromagnet. Now, as soon as we introduced the ferromagnetic core, what happened? It had a magnetic flux of its own. It added to the pre-existing magnetic flux coming from the coil. It became additive. Our magnetic flux density increased in proportion to it. Now, in our demonstrations where we saw that our subject was trying to tear apart the electromagnet while it was energized, and we had current running through, and we also had magnetic flux flowing through the coil as well as throughout the body of the core material, creating a path for magnetic flux to flow. It was demonstrated that the more current that we had in the circuit, the stronger the magnetic field was, or the flux density. And progressively, as we took batteries away, we started to weaken the amount of current flow, and as a result, the flux density went down until our test subject was able to withdraw this quite easily. Now, what was the upper limit, or how strong could we make an electromagnet? Well, that's going to be determined by the core material, or what the core material is made of. Now, there are different types of materials out there. Alloys called relay steel, alnico, that have better magnetic properties than other pieces of material that we can make a core. But more importantly, it's also what we call the saturation point. The ability of the core material to concentrate those magnetic lines of flux. If we were to add more and more current, there comes a limit where the core material is going to reach its saturation point, and we could increase the current as much as we want. You're not going to see a significant increase in the strength of the magnetic field. But that being said, what are some of the things that we can do to affect the strength of an electromagnet at the design stage? Meaning, if I want a stronger magnet, what are some of the things that I can do when I'm designing this? Well, a few things come to mind. I could increase the number of turns of wire. That's one strategy. I could also increase the current flow to the coil, but that's going to mean then that when I build my coil, I got to make sure I have a large enough gauge of wire to withstand that. Looking at some of our textbooks, they also talk about, could we increase the square area of the core? That the saturation point of the core would be affected if I actually had more mass. And finally, what the core is made of. There are steels or alloys out there that will perform better than others. We have such exotic metals as alnico, relay steel. Steel that actually features 1% silicone is also something that you'll read in your textbook. They found that by adding 1% silicone, the material actually had better magnetic properties. So there it is in a nutshell of some of the effects or issues that will influence the strength of an electromagnet. I hope you found this informative. I really enjoyed putting this together for you, and hope that you will tune in to many more of our videos. Until next time, stay safe.